Hello, my name is David Walgren Parent, and I used to teach 122. I'm the lab coordinator, and I think you might need a hint on doing differential equations to op-amp circuits. I say this is the easy way, but it's still a complex thing. But it's not as complex as it might look. So here's a quick design flow to take differential equations into op-amp based circuits. And the first thing is change the differential equations to integral equations. And I'll more on that later. You can then make behavioral models to check slew rate limits, and that's in other videos that I've done. Start with the simplest integrator with an initial condition. And each variable, each time-dependent variable, only needs two op-amps, an integrator and an initial condition op-amp. Now, there are other methods that are more advanced, and you can get away with one op-amp, but that's beyond the scope of this. Then, once you have your integrator, you choose an R and C values for this integrator, and you try to use a common value for the capacitor for all the values, and then solve for the different R's. Use the universal op-amp model then to check for offset voltage, gain, bandwidth limitations, and finite open loop gain problems. Then once everything's working there, you can use the LT-SPICE model, meaning if you're using a 1006 or some other op-amp, you can use their model directly. It won't simulate offset voltage, but it will simulate the fact that there's a minimum RL required for most op-amps, which is about 2 kilo ohms. So let's just do what I would consider a simple example. I have X as a time varying variable. X naught is an initial condition, and I want that to be 1 volt. Here is the differential equation, and I convert it to integral form. And the reason is that when you differentiate a signal and there's noise, you can create large voltage swings that will corrupt your signal. Integrals tend to smooth out noise. So in this case, just X is the initial condition plus the integral of X. There's no scaling here. So the RC constant is really just 1 second. So that time constant is so slow that I'm not going to make behavioral models right now to check for slew rate issues. I'm just going to jump right in. And I'm going to use a simple integrating core of an inverting integrator and an inverting summer, because this will give me minus the integral of X, and then this will invert it, and then it will invert my initial condition. So let's look at the design equations. So I have X naught, which is this node here, is 1 over R1C1 integral of X, and then X is R4 divided by R2 inverted, and R4 divided by R3 gives me my initial condition. Now there's only 2 equations and there's 5 unknowns. Now in the past I've said R4 maximum is 1 mega ohm, so that's something we can think about. Now let's look at the integrator first. R1 times C1 equals 1 second. So we have a lot of choices. C1 could equal 100 microfarads, then R1 equals 10 kilo ohms. If C1 is 10 microfarads, then R1 is 100 kilo ohms, and so on. Now, I'm going to choose C1 equals 10 microfarads because that's an easy to get capacitor in the lab, and I've used it in the past. Also, R1 right here is the load of U2, and so it has to be above 2 to 10 kilo ohms depending on the op-amp, because R1, right, that's connected to virtual ground, is the load of that op-amp. Okay, so again, to summarize, R4 could be, the maximum is 1 mega ohm. I'm not going to put it there yet. Now, the output of the integrator doesn't need scaling, so R2 and R4 can be equal, meaning I'm already getting not X here, so if R2 and R4 are equal, then X is just the inverse of not X. Now if I want to minimize the power, I can set that to 1 mega ohm. If I want to minimize noise, I can set them equal to 10 kilo ohms. Now X naught is 1 volt, and I can just hook up the power supply there and keep R3 equal to R4 and not scale it. Thing is when you do that high march rolls, you will run out of power supplies. So it's better to scale your 15 volts or your minus 15 volts to the proper initial condition. So since we're using an inverting summer, okay, we can take a positive voltage and turn it into a negative, or we can take a negative voltage and turn it into a positive. So I'll take a minus 15 volts, I'll put it here, and design R3 and R4 to give me 1 volt. So V out due to X naught would be minus R4 divided by, actually that should say R3. I'm not going to stop the video for that, but I'll fix it in the notes. So R3 should be, I'm going to just set as 150 kilo ohms, solve for R4 10 kilo ohms, and then that makes R2 10 kilo ohms. So then here's our design, 10, 10, because NX doesn't need any scaling, minus 15 times 10 divided by 15 will give me 1 volt. Now I might want to filter these power supplies with a low pass filter because they can be noisy. All right. Now here's my working simulation, and you can grab this and put it into your computer and see if it works. Now U1 minus is the node name right there, because sometimes you need initial conditions to short this capacitor to 0 volts. You might even need a wire to do that in your real circuit. And you can see that it matches pretty well right up until about the power supply, in which the op amps saturate, but this behavioral model doesn't. I could add V offset problems or other things to simulate, but not going to do that at this time. Now let's do a different example where we have a derivative of x equal to minus x. So I convert that into integral form. I use this simple integrator core again. Now we've already designed this for a time constant of 1, but now we are going to keep this inverted. So if this is a minus, then and we put it through a positive summer, it's going to still be minus. If I have a positive voltage now here, it will keep it a positive voltage. Now we need to redesign some of these resistors. Okay, and so if I set R4 equal to R6, and then I keep this ratio here, then I can use this design equation where Vx equals R6 divided by R2 times Vnx, and R6 plus R6 divided by R3 times V plus. I've got to maintain this ratio, and R4 has to equal R6. So I want a ratio of R6 to R2 equal to 1, and R6 to R3 equal to 1 to 15. So if I keep the R6, 4, and 2 equal to 10 kilo ohms and solve for R5, I get 9,375 ohms, which of course you'd have to round to a real value in the kit. When I simulate, it matches pretty well. In this other example, it has two variables, where X is now fed into the Y circuit and Y is fed into the X circuit. And it's the inverted case, where we're integrating minus Y and integrating minus X. You can see the behavioral models take that into that account as well. One more example is we're not inverting anymore, and really I just use the same thing as the where x equal to x naught plus the integral of x, and we get the same result, where once it saturates, that's where the check voltage and the op amp voltage deviate. Now here are some hints. Integrators can be summers too. I can sum x and y into this variable, and in this case because C1 and R9 and R1 are the same, I can keep the time constant of 1 second. We even have another hint, is that they can sum and subtract. So in this case, I'm subtracting and integrating VA and VB, but I'm adding the integral of the voltages at C and D. Now this equation will work out if I keep C1 equal to C2 and I keep these ratios. Now sometimes it's not going to work out and you'll need an extra gain term. So if this side turned out to have a larger gain than this side, I could add another resistor and just tie it to ground. Same thing here. If I can't get this gain to equal the sum of these gains, or these ratios, I just add a dummy variable and set it to ground. And it works quite well. And if you walk around the building, you can see circuits where people have done that. And here's the final thing. Each time-dependent variable only needs 2 op amps. One inverting or non-inverting integrator and one inverting or non-inverting summer for the initial condition. And just like this is an integral that subtracts and integrates A and B and adds C and D, the integral, if I put a resistor here, I could get I could be adding and subtracting signals all at the same time. So if the Hindmarsh Rose has a variable of X, Y, and Z, you only need 6 op amps to get that to work. And I hope these hints help. And good luck with your circuits.